Hello everyone, this is the second edition to the matrix decomposition series, and today we'll be looking at the permuted LU decomposition. This slightly generalizes the LU decomposition to include matrices that require permutations to reduce. And we're going to do this by simply tracking all the permutations that we do, just like we did for the eliminations in the LU matrix. This is an example of a matrix that requires the permuted LU factorization and cannot be factorized with just the regular LU factorization. As you can see, there's a 0 in the 1, 1 position, which is a pivot, and this prevents us from eliminating any of the other elements below it. Hence, we must permute this row with the first row that is non-zero below it in order to get a non-zero pivot. Note that the permuted LU decomposition can only be done for square, non-singular matrices, but it can be done for matrices that aren't necessarily regular. Okay, let's see this process of doing a permuted LU decomposition with an example system. So consider the following a linear system. We can rewrite this in matrix form like so. To solve this system with the permuted LU decomposition, these are the steps we will take, starting off by simply finding P, L, and U. To do so, let's first write three matrices. The first matrix is just the A matrix, and this will eventually become our U matrix. The second matrix is a half-filled lower unit triangular matrix, and this will become the L matrix. These two first matrices are the same as the LU decomposition, but now we add an additional third matrix, which is a 3x3 identity matrix, which will eventually become our P matrix. Now let's reduce A. This time we must not only track the opposite of the coefficients we multiply the rows by, but we must also track the permutations that we do. We see that the first pivot is non-zero, so we don't have to permute. We can simply do a regular row reduction. We will multiply the first row by -2 and add it to the second to eliminate the 2, 1 entry. Now we track this elimination in L by writing the opposite of the multiple we used. So we simply write 2 in the 2, 1 entry of the L matrix. The P matrix will stay exactly the same since we didn't do any permutations. Now the 3, 1 entry is already a 0, so we have eliminated everything for the first pivot, and we can track this by simply putting a 0 in the 3, 1 entry in the L matrix, and again the P matrix stays the exact same. Moving on to the next pivot, we see that the 2, 2 entry is a 0. This is a problem, and now we will need to do a permutation to get a non-zero pivot. Now I'm simply going to swap the second row with the third, and as you can see now we have a non-zero pivot in the 2, 2 position. Note that you only want to do swaps with the row below the current pivot row and nothing above, since the rows above have already been reduced. We must track this permutation in our P matrix, and we will do so by swapping the rows 2 and 3 of the P matrix. And then lastly, we must also change the L matrix to reflect the new position of the previous elimination. And we will do this by swapping just the 2, 1 element with the 3, 1 element, and not the whole rows. Okay, lastly, we would need to eliminate the second or the element right below the second pivot, but since this is already a 0, we are done, and we can add our final entry to the L matrix, which will be a 0. With that, we have found L, U, and P, and we can utilize the fact that P times A equals L times U, and we can use this to solve the system. If we multiply AX equals B by P on both sides, we get PA equals PB. Now we can substitute LU for PA, and we get that LUX equals PB. And now we just have a system with the lower triangular matrix times the upper triangular matrix, and this is just like solving a system with the regular LU decomposition. So if you don't know how to do this, check out my last video. Alright, that is all for today. In the next video, we'll be going over the Cholesky factorization. Thank you.